annoying you?
No, I thought she was acting.
There we go. Fresh air. Makes us all happier. So, what's my transformation on A? Down 2. I gave you an actual graph this time instead of an equation, so we couldn't just necessarily make a T-chart. If we were stuck on this one, we have to kind of know our transformations. But all we need to do is take some points that we can tell on this graph, so some of the nice, easy points, and just shift all of them down 2. Like that. What does B do? So every point goes right. Okay. What's C doing?
Left 1, up 2.
Good. So, 2 transformations, left and up. What about D?
Reflection of X. R2.
Okay. That negative out in front is like making all of your y's negative, so we flip or reflect over the x. The -2 moves it right 2, and the +3. Which one do we need to save for last?
The up 3.
Right. Save your up and down for last, especially when you have to flip. It won't make a difference otherwise, but when you're flipping, if you moved it before you flipped, you might throw yourself off. So, if I flip this point over the x, it doesn't go anywhere. Right 2, up 3. If I flip this over the x, it goes down to -2. Right 2, up 3. Take my 0, 0, flipping won't change it. This is 1, -2.5, so when I flip it goes to 1, +2.5. Right 2, up 3, kind of goes off my graph there. And then the final one. Any more questions on this? So that's kind of a recap of what we were doing Friday or Thursday. So let's get into the symmetry. There's different kinds of symmetry. So the first, you can be symmetric to an x or y axis. Symmetric to the y axis means you look the same on both sides of the y axis. If I fold my graph on the y axis, it doesn't overlap, or it overlaps itself. What that says is, in terms of your points, a positive and a negative x value give you the same y value out. So like a quadratic, we know if we do 2 squared, we get the same thing as -2 squared. Symmetric to the x-axis means if I fold this graph on the x-axis, it overlaps itself. Is this one a function?
No.
No. what that means is a positive and a negative y give you the same x value out. So to check for these symmetries, all we really have to do is either graph it and look at a graph, or plug in a negative for the opposite variable and see if we get the same equation back. So I'm going to practice some algebraically. I may do some both ways, but on A, is that one we could even put in our graphing calculator? No, it has to be y equals to plug it in. So we would either have to make a t-chart to graph it or just work it out. So to check symmetry to the x-axis, what we're going to do is replace our y with a negative y. So if I do that, when you do the absolute value of a negative, what happens? Is that the same equation I started with? Yes. So if you do it and you get the same thing back, then it does have that type of symmetry. So this graph is symmetric to the x-axis. To check the y-axis, you replace your x with a negative x, so make the opposite variable negative. If I do that, is there anything I can do to this to turn it back into the original equation? No. So it is not symmetric to the y-axis. Is that okay? I'm probably not going to do all of these. I'm going to jump around and do a few of them. Let's do maybe C and D, and then we'll do more if we need to. So to check the x-axis, is this one we could graph on our calculator? Yeah, you could solve for y and graph it. How do you check symmetry to the x-axis? Okay, so I get 2x plus y equals 6. Is there anything I can do to that to turn it back into the original? No. So it is not symmetric to the x-axis. Y-axis, plug a negative in for our x. So we get a negative 2x minus y equals 6. Is that what we started with? Nope. Can I turn it into what I started with? Nope. So this one doesn't have either kind. It's possible to get one of them to be yes, it's possible to get them both to be no. Let's do D. So to check the x-axis, we make our y negative. What happens if you square a negative? Makes it a positive. Is that what I started with? Yes. So this one is symmetric to the x-axis. To check the y-axis, we have to make our x a negative. When we square a negative, that becomes positive again, so this is also a yes. So they can both be yeses. They don't think it's one or the other. You might have all yeses, you might have all no's, you might have one of each. Do I need to do more like that? The third type of symmetry is symmetry to the origin. So if it's symmetric to the origin, you're going to replace the x with a negative x and the y with a negative y. An example of a graph that's symmetric to the origin is the cube function. Basically, if it's symmetric to the origin, you have to flip it over both the y and the x-axis, and then it overlaps itself. Okay, so it takes two flips, and then it overlaps. So we're going to do a couple and just check the symmetry to the origin on those. So you replace your x with a negative x and your y with a negative y. So negative x squared is positive x squared. Negative y squared is positive y squared equals 16. So it gives me back what I started with. So this one is a yes. Do you guys know what this graph is? X squared plus y squared equals 16? It's a circle. That one's just a circle with a radius of 4. So if I could draw, my circles always look like footballs, so just pretend that I drew it evenly. But you could see it has symmetry to the x-axis, the y-axis, and the origin when we're looking at that circle.
I think it looks like a lemon.
Huh. See, usually they're footballs. Today it's a lemon. I'm getting better. Slowly. Alright, this one. If I want to check symmetry to the origin, we make both our x and our y negative. If you cube a negative, what does it become? A negative. Okay, that's not what I started with. Can I make it what I started with? How? Either multiply or divide by -1. And that one is also a yes. Are you guys okay with the symmetry? There is a slide. This is in your book, and so I put it up here. This isn't necessarily anything you have to remember. Basically, it's telling you some properties of symmetry. If you check symmetry, we have 3 different types. You might get all 3 of those to be no. We might get all 3 to be yes. You will never get 2 yeses and 1 no. You can get no yeses, 1 yes, or they're all 3 yeses. But you'll never get 2 out of the 3 to work. Does that make sense? And it is possible to be symmetric to the origin, but not symmetric to either the x or the y axis. So that's really all that says. Again, you don't really have to memorize that, because as long as you know how to check all the different types of symmetry, you'll be fine. Along the lines of symmetry, if we're looking at functions, instead of saying symmetric, a lot of times we talk about even versus odd functions. And it's really the same principle. If it's a function, can it be symmetric to the x-axis? No, so it fails the vertical line test. So even is the same thing as symmetric to the y-axis. Odd is symmetric to the origin. So I just remember that the O's go together. Odd is origin, even is the y-axis. Can't be a function and symmetric to the x. So we can check this the same way But a lot of times it's written in function notation already. So all we really have to do is plug in a negative for our x. If it's even, that's the same as symmetric to the y. We said a positive x and a negative x give you the same answer, right? So if it's even, you should be able to plug in a negative and get the original function back out. Odd, you had to put in a negative x and a negative y. So if it's odd and we put in a negative, we should get the exact opposite of what we started with. So again, it's kind of the same thing, just written a little differently because we have function notation. Let's look at some graphs first and make sure we can decide if they're even, odd, or neither from the graph. So the first one. This one is symmetric to the y-axis, which is the same thing as even. What about the second one? That one's symmetric to the origin, right? You'd have to flip over the x and the y before it overlaps, so that is odd. Okay. This one. Yeah. If you think about it, like if I took just these pieces, if I flip them over the y, then it would look like this. And then if you fold that on the x, don't they overlap the rest of the graph? So that one's symmetric to the origin as well, which is odd. And what about this one? Symmetric to the origin again, so that's odd. So looking at a graph is pretty easy. In terms of functions, functions are always going to be something you could plug in the calculator, so you could look at a graph and tell. I just want to do a couple examples checking by hand, and then I'm probably going to stop there. So I am asking you to algebraically do it. We can confirm that with the calculator. To check even and odd, all we're really going to do is find f of negative x. So if I plug in negative and for my x, if you square a negative, it is. So we got the same thing that we started with. So that means it is symmetric to the y, which is even. If you graph this, this is just a parabola shifted down 5. So couldn't we confirm that that was in fact even? B. So if we plug in our negative x, if you cube a negative, it is. Okay. The rule is, if it comes out to be the original, it's even. If it's the exact opposite, like multiplying the original by -1, it's odd. Is this the same as multiplying the original by -1? No, it would have to be a negative x cubed plus 1 for that to work. So what does that mean this one is? Neither. If you think about the graph, this is just x cubed shifted down 1. And so we can see it doesn't have the symmetry. Last one. So if I plug in a negative for my x, if we cube a negative, it is minus negative x plus x. So we get negative 5x cubed plus x. Is that what we started with? Is it the exact opposite?
Yes.
So that means it is? practice with this stuff. I'm okay with it. So that's the end of the section. The homework is printed on your notes handout. And we have a lot of time left for you guys to work on this homework and ask me for help when you need it. Okay? It is due tomorrow.
Do you have a quiz tomorrow?
Yes. So tomorrow, we're turning in the Section 7 homework. We are also taking a quiz over Sections 6 and 7. So Section 6 was all of our parent function stuff, which the good news is when you're practicing your transformations, you're practicing all of that. We talked about increasing, decreasing, and constant, that section as well. So you can expect, I might ask you some questions about those graphs. If you remember in section 2.6, when you guys did the homework, you flip your book to page 255. We have a lot of questions about the graphs. You know, what's the domain? What's the range? Where is it increasing? Where is it decreasing? So you can expect me to ask you any of those questions. Being able to look at a graph and answer any of those. Transformations, like you're doing on your homework tonight. So I would expect a parent function with a minimum of 3 exact points. You draw that dashed, and then you draw your transformation, shift it over with your 3 points. The other thing that we may need to review, we did piecewise functions. Do you guys need a recap on how to graph a piecewise function? No? You guys know you make a T-chart for each piece. You'll start at your endpoints, either open or closed, so expect to have to graph at least one piecewise function on there. Okay? So we'll do that tomorrow, and then we'll move on with the next section on Wednesday.